Rasa community, and welcome to the reading group. We're going to be continuing with a paper today, and that paper is Recent Neural Methods on Slot Filling and Intent Classification for Task-Oriented Dialogue Systems, a survey by Samuel Louvan and Bernardo Magnini? Magnini? I'm probably saying it wrong. I apologize. If anyone knows, please feel free to tell me in the chat and I will correct it. I do know IPA, so the International Phonetic Alphabet. So if you know what it's supposed to be and you could write it phonetically, that would make my life easier. Last week we got started with this paper and we talked a little bit about what the task is. So intent classification is something that we do in Rasa, and this is for each turn where a user is talking to an assistant, identifying what it is they want to do from a predetermined set of classes. And then slot filling is slightly different from what we do at Rasa. So for us, slots are pieces of information that you store across the whole conversation. In this literature, hey Amina, good to see you. In this literature, slot filling is the slots are associated with specific intents. So if I want to book a train, I would need to say like where from, where to, and like the day that I was interested on it, and all of those slots would be collected. So they're similar, but they're like slightly different. The introduction talked a bunch about sort of the different like what slot filling and intent classification is, and then background of various ways that people have tried to do it and where intent classification comes from, and then talking about the scope, and then some of the data sets as well, and we'll come back to these as we go through and look at the system evaluations. And then the last thing that we looked at, get out of here. Oh, you're more in the shot. Well, okay. I've got a mic. That is not a surprise to anyone. It's right there. And then we went through, hey Robbie, the first set of approaches, which were all independent models. So you have one model for slot filling and one model for intent classification, and then you use them together. And just to quickly go over what the findings were there, folks tried a lot of different things, some early work on convolutional neural networks, but the best results were with recurrent neural networks. I feel like there was another point I was trying to make there. Yeah. And bidirectional encoders were better than the unidirectional encoders, and of the unidirectional encoders, LSTM, long short-term memory, it's a particular flavor of recurrent neural network, were the best performing, which this was probably, like when I was getting into NLP, this was sort of the thing that people were talking about were these bidirectional LSTMs. More context improves slot filling, so using global context and attention mechanisms improves it even further, so bidirectional LSTMs with attention. Adding semantic features were more helpful than syntactic features. By syntactic features here, I believe specifically they were referring to part of speech tagging. And it's related to named entity recognition. So we do entity recognition in Rasa, and entities can go in slots. Not all slots have to be filled with an entity, and not every entity has to go into a slot. But the approaches used for named entity recognition can also be used for slot filling because there is overlap in these particular approaches. And there's a survey there. And then the big disadvantage of independent models is that they do not exploit the interaction between intent and slots and may introduce error propagation when they are used in a pipeline. So this is two different models. The most recent paper in this line of research was in 2016. And then the thing that came after it, because this is being a very organized chronologically. I was trying to make duration into a noun to describe something, but it's not actually organized by duration. It's organized chronologically. Were joint models. So you have one model that does both. And let's start reading, and then we'll pop up to look at the figure when it is relevant for us. In section 3, we reported approaches that treat slot filling and intent classification independently. However, as the two tasks always appear together in an utterance and they share information, it is intuitive to think that they can benefit each other. For instance, if the word "the Beatles" is recognized as the slot artist, then it is more likely that the intent of the utterance is play song rather than book flight. On the other hand, recognizing that the intent play song would help recognize Hey Jude as the slot artist rather than movie name. And I don't actually know if there's a movie called Hey Jude, so I don't think these are ambiguous, right? I think if you can detect the entity, it will be unambiguously mapped to one type of piece of information. Recent approaches model the relationship between slot filling and intent classification simultaneously in a joint model. These approaches promote two-way information sharing between the two tasks instead of one-way pipeline. So pipeline is, one component feeds into the next, feeds into the next. So if I know something in step 2, it can't affect my understanding in step 1, right? There's a unidirectional flow of information. We described several alternatives to exploit the relationship between slot filling and intent classification through parameter and state sharing and gate mechanisms. I'm trying to think where, because we haven't read the third section yet, and the algorithm that we've developed at Rasa is the diet algorithm, which I think. Sorry, I'm just quickly scrolling to see. I think this would probably be the closest to the diet algorithm of the approaches that they discuss. I would call it multitask learning rather than joint learning, and I'm wondering if there is a difference. So I'm just going to look that up in another joint learning versus multitask learning. I think I'm gonna look this up before I say it. I'm pretty sure joint learning has 2 objectives, whereas multitask learning has 1 objective, but multiple things can be updated based on it. I'm on Quora. What are the differences between joint learning and multitask learning? Blah, blah, blah. Nope, these aren't actually helpful. The answer was incorrect. Multitask and multilingual joint learning. They allow us to accumulate just shareable knowledge. Joint multitask learning. I'm on Wikipedia. An approach to inductive transfer that improves generalization by using the domain information contained in the training signals of related tasks as an inductive bias. It does this by learning tasks in parallel while using a shared representation, which is learned for each task can help the tasks learn better. And I'm just gonna search for for example, the explicit learning of sample relevance across tasks can be done to guarantee the effectiveness of joint learning across multiple domains. Are these synonyms? Joint learning of unrelated tasks which can use the same input data can be beneficial. I think that these might be synonyms. I think that this is probably where diet would fit. And I'm sure that there are places where people would use the terms differently, but based on sort of my reading previously and my quick search, it looks like here multitask and joint learning would be considered the same thing. I guess the difference is joint learning, you could be learning the same task twice? The different inputs, I guess? I don't know. Anyway, the point is, I'm pretty sure that this is where this would fit in. This is where diet would fit in this particular paradigm of discussing models. All right, parameter and state sharing. A pioneer work in joint modeling is Sue and Sorikia. Not entirely sure how to say that either. Which performs parameter sharing and captures the relation between slot filling and intent classification through tri-CRF. The model uses CNN as a shared encoder for both tasks, and the produced hidden states are utilized for slot filling and intent classification. Okay, so you've got the encoder is shared, so the input is put into a single model component, which in this case is a convolutional neural network, and then those hidden states are used for multiple tasks at the same time. So yeah, here I think you would have multiple reward functions. In addition to features learned from the neural network and from the slot label transition, tri-CRF incorporates an additional factor G to learn the correlation between the slot label assigned to each word and the intent assigned to the utterance, which explicitly captures the dependency between the two tasks. Okay, so there's another task as part of this where, given these slots, what are the most likely intents? Given this intent, what are the most likely slots? Correlation. Yeah, I don't think it's like a directional dependency. I think it's in both things are considered as affecting the other. A similar approach, Guo et al. 2014, shares the node representation produced by a recursive neural network, RecNN, which operates on the syntactic tree of the utterance. The node's representation is shared between slot filling and intent classification using a shared by-GRU encoder and a joint loss function between slot filling and intent classification, figure 1 left, in which the loss function has weights across each task. Okay, so here we have a single loss function that is weighted between the two tasks. And the recurrent neural, sorry, this is not recurrent, this is recursive. I vaguely remember reading about these. I remember nothing about them, about the recursive neural networks. So an RNN is a recurrent neural network, and a RecNN is a recursive neural network. So I'm guessing recurrent just steps over a time series. The big difference is that a recurrent neural network doesn't just step over a time series with no explicit relationship between points in a time series, but this one handles the hierarchical relationship between things in a syntactic phrase. So a lot of times you'll see syntax represented using a tree, like a decision tree, usually binary, and basically the more closely two things are connected in the tree, right? The closer siblings they are, the stronger the relationship between the two words or between the phrases. So the classic example is like, I saw a monkey with my spyglass. If the monkey has the spyglass, right, then you'd attach those things close together. If I have the spyglass, then I'd attach those things close together, and it would have a different internal structure. And you could draw, one tree for each of those, and the hierarchical structure would capture that ambiguity. That's a very, and that's syntax. That's all of it. That's all you need to know. I'm kidding. Syntax is a full field. Is there any benefit if we found the relationship between slot filling and intent classification? What can we achieve? Does it improve NLU? Yeah, so I think the big point that they're making here as they start to talk about this work is that slots and intent classification are not independently distributed. And I mentioned in Rasa, slots are sort of for us, are a conversation level thing, right? That you would select from anywhere in the text, you might anywhere in the conversation, and can be filled in a variety of ways. Here, slots are like specifically tied to particular intents. and they're not independent, right? So there's a relationship between a slot and an intent. So if I am, you know, booking a train, I'm not going to also at the same time be asking for the title of a movie. That was a weird example. It was sort of parallel to the example that they gave. So having information about the slots or having information about the intent can inform our decision in the other one. That makes sense. There's a dependency between them. So this is the model that they are using. So shared by GRU encoder. So GRUs are gated recurrent units, bidirectional, so they go left and right. Okay, and then it looks like at each at each word or each token. So this is very similar to diet if you haven't done that. Whether or not something is an whether or not something is an entity is a token level measure. And then also there is a intent label for the whole thing. And I don't think we've gotten to the slot gated mechanism yet. So this is sort of the first approach that they are talking about from 2016. This one with the joint loss function. Liu and Lane, 2016, used a neural sequence-to-sequence encoder-decoder model with attention mechanism commonly used for neural machine translation. So this was the thing that was really popular when the transformer paper came out. So the original transformer paper, Vaswani et al., 2017, was about was proposing a way to do sequence-to-sequence modeling specifically for machine translation. So this predates that. With attention mechanism commonly used for neural machine translation. The shared encoder is a bidirectional LSTM, and the last hidden state of the encoder is then used by the decoder to generate a sequence of slot labels, while for the intent classification, there is a separate decoder. So usually the way that sequence-to-sequence works, same as with the transformer, is you have an encoder, which basically takes text and turns it into numbers, and you have a decoder, which takes numbers and turns it into text. And that could be, you know, a string of output, like it is for, the large neural language models. It could be a label. It could be... Those are usually the two things it is. It's usually text input or label output. Text output or label output. And they are using the same decoder for both of them. They're using the same encoder and then a separate decoder. So that's the same architecture more or less as they were using up here, where the convolutional neural network is being used as the encoder rather than the LSTM. The attention mechanism is used to learn alignments between slot labels in the decoder and words in the encoder. So very... I was going to say similar to a transformer, not really similar to a transformer, actually, but the labels in the decoder and words in the encoder. Okay, so in the decoder we have specific slot labels like source destination, target destination, etc. And then words like, you know, Paris, Berlin, Milan, or whatever it is. And then the attention mechanism is used to link those two. Akanitur et al. Also adopt parameter sharing, similar to Zhang and Wang, but instead of using GRU, they use a shared LSTM and perform prediction for slots, intents, and also domain. So basically, slight iterations on this general paradigm, this general architecture, which, I mean, that tends to be how NLP research works in the neural age. RNN is only useful for sequence data. Yeah, that's generally when it's used. And I would say, again, I'm not super familiar with recursive neural networks, but LSTMs are definitely a flavor of RNN. And we haven't gotten to this one yet. In a recent approach by Wang et al., 2018, proposing a bimodal-based structure to learn the cross impact between slot filling and intent classification. So like I mentioned, there's not, you know, a single directional relationship between slots and intents. They can both inform the other. So an example of a single directional relationship would be weight as a puppy, weight as a grown dog. So as, you know, the weight that a dog is as a puppy will affect its weight as a grown dog. So if a dog, you know, is from a smaller breed, then that's gonna, well, that's a latent variable. But let's say within a litter, the smallest puppy is probably gonna grow up to be the smallest dog. But, you know, maybe the smallest dog got adopted and by somebody who just like loves to feed it, and maybe it's a little bit overweight. The heaviest dog does not mean that that dog was also the heaviest puppy, right? There's a causal relationship there, but it only goes in one direction. In this case, the causal relationship goes in both directions. I don't know. I hope that's making sense. Sometimes it can be hard to come up with examples for developing probability intuitions on the fly. They argue that a single model for two tasks can hurt performance, and instead of sharing parameters, they use two task networks to learn the cross impact between the two tasks and only share the hidden state of the other task. Interesting. In the model, every hidden state H1T in the first network is combined with the hidden state of the second network and vice versa. Training is also done asynchronously, as each model has a separate loss function. Quinn et al. Used a self-attentive shared encoder to produce better context-aware representations, then apply intent classification at the token level using this information to guide the slot filling task. They argue that previous work based on single utterance level intents prediction is more prone to error propagation. If some token level intent is incorrectly predicted, then the other correct token level prediction can still be useful for the corresponding slot filling. For the final intent classification prediction, they use a voting mechanism to take into account the intent classification prediction on each token. Okay. So these are pretty different approaches. Also, you may say, Rachel, 2018 is not that recent. I believe this paper is from 2020, late 2020. Yeah, late 2020, December 2020. Also, this type of thorough evaluation of previous work generally is part of a dissertation, so I would not be surprised if this is one of these two authors' dissertation. I mean, it could just be that they're writing it as a helpful survey for all of us, in which case, thank you. But if it is a dissertation, it is not rare for it to take a while, a while for it to be written. Okay, so this is interesting here. And then I'm just going to finish this, and then we can talk about the particulars of the argumentation of the other researchers here. Chen et al. Used a transformer, Biswani et al. Model for slot filling and intent classification by fine-tuning a pre-trained BERT model. The input is passed through several layers of transformer encoders, and the hidden state outputs are used to compute slot and intent labels. The hidden state, HCLS, is used for intent classification, while the rest of the hidden states at each time step serve for slot filling. Sorry, IC and SF are both acronyms that mean other things to me primarily. So SF, San Francisco, and then IC, individual contributor. So it takes me a minute to say the right words when I look at them. This, I would say, is very much... Usually when a new big architecture comes out, there's like a big rush of papers of people applying the architecture to different problems and seeing how it works. And that is very much what I expect. It's not that it's not work, not that it's not good to do and interesting and helpful, but this paragraph is like, yeah, of course, that's what they did. The previous paragraph, now, there are some really interesting claims here that I think a lot of current researchers probably wouldn't automatically make. Enrique says, more recent work today. Yeah, we're moving up through time. Hi, Faiza. Good to see you. So here, if you are familiar with, for example, the GPT-3 paper, right, or there's a sort of general trend in NLP research overall that's moving towards training one really big model that's quote unquote general purpose. So an example of this would be, GPT-3 or T5 or honestly BERT. So big models that are designed to do lots of things. And arguing instead for smaller separate models is very much like, it's not a contrarian position, but it's something that is kind of against the mainstream approach to doing NLP research right now. But there is a fair amount of evidence that this is the case, right? That super big multitask learning where you're doing a lot of things can hurt performance on the individual tasks. So a good example of this would be a recent paper. I retweeted it. I forget where it was from. Looking at MBERT, which is multilingual BERT, and showing that you can use far less data from a specific language to train embeddings for that specific language than trying to train a large multilingual model. And you'll actually have worse results for each of the specific languages that I think was not the main language that was trained with. So there's sort of a assumption that if you just have enough data, you'll be able to do transfer learning, and what you transfer will be helpful for the specific task. So the idea that like, hey, that's not necessarily actually the case, and I don't know that they're talking specifically about transfer learning here. It sounds like they're specifically talking about these two tasks. Is really interesting. And so the way that they're getting around this is that they are training their networks separately, but you can sort of like, the networks can peek over at each other to see what the other network is doing, to look at the hidden weights of the other network. And then this is also interesting, the Quinn paper. So they are looking at things at the token level. So slot filling, you would do at the token level, like, does this token go in this slot? But they're also doing intent classification at the token level, which makes sense to me because not every token is going to be equally informative to the particular slot, to the particular intent classification class. So a good sort of example here is like an extremely common word in English. We've got one there, we've got one here, we've got one here, we've got one here. So the token the for intent classification is going to be pretty much meaningless. That's why it's often removed along with other very, very common words in English, at least using stock words in earlier work, because they're just not that informative. Whereas something like words like book, flight, destination, travel would be very informative if I am learning about the destination that we're traveling to, or trying to book a flight or something. So this sort of token level intent classification, it is a label that is generally applied at the utterance level, but they're sort of using an ensemble voting model here, where presumably the tokens that are very informative are going to get a really high weight towards a specific class, and then using that information in addition to the slot filling information to try and correct or get ahead of errors in intent classification. I was talking about this with Adam, I think he's the head of research is his title, the other day, that like a lot of the big neural network methods are really bag of word methods. And if you happen to have a word that only shows up in one class in your training data, even if it's very spurious, even if it's not an actually helpful clue to the content of the message, or it's not one that a human would use, it can still lead to your results being funky. So this sort of ensemble model, I think, would still be susceptible to that type of problem, but it's interesting, right? It's a different approach, and I'd be really interested to see sort of what the authors are up to now. I mean, this was 2 years ago, so I imagine that more work has been forthcoming. Anyway, yeah. Let me see what the chat says. If you're going to combine an NLP model, then it needs more compute. GPT and BERT are highly computational models. They generate more COT than computer vision. Computer vision it depends. I read in Sustain NLP. Yeah, that's a great paper if you haven't read it yet. Yeah, that's a good question. So yeah, the big transfer learning models do need a lot of parameters because generally the more complex a task and the more types of things you want to be able to handle, the more weights you're going to need, the more parameters you're going to need, the longer it's going to take to train. And there's this problem called over-parameterization, which is having too many parameters, basically, having too many weights. And it's been something that, particularly in the transformer literature, particularly in the Bertology literature, has come up again and again. So you can remove most of the weights in a BERT model for a specific task and see no change in performance. We read Anna Rogers' paper a while ago that talked about a lot of those studies there. But the rub is that you aren't, if you want a single model that you can sort of prune down to a bunch of different models, then you do need all those weights. Seems to be the case so far. Yeah, I mean, we're very much, we're in the weeds of figuring out what works and what doesn't as a research community right now. Popping Tonic says, could a gating mechanism be used to make parameter sharing easy, similar to multitask learning models? Yes, and we actually haven't gone back up and we haven't seen this one yet, but certainly the earlier models, like the Zhejiang and Wang one, were using a gating mechanism. So they were using GRUs. Machira says, how can I use other pre-trained models with the natural language toolkit? Oh, an LTK. How can I configure config.yaml for pre-trained model for other languages? I don't want to get too off topic. I should have a little forum pop up. Yeah, I would ask on the forum, and what you're going to want to do is you're going to want to build a custom component to add to your pipeline, and we have more information about that in the docs. But if you would like more information on like specifically what you're working on, I'd ask on the forum. Yeah, there's a lot of languages that have like supporting components in NLTK that don't have them in Spacey or other libraries yet. All right. Slot intent gate mechanism. Wow, we're already halfway through. I don't know how far we're gonna get. We might get through. This might be a 3-week one. I know the interesting thing about survey papers is that they pull together a lot of ideas and they can be very helpful in that way. But the sort of the challenge as someone who is reading them to you is helping to provide additional context that the authors of the paper assume you already have, but you may or may not. Also, it's just interesting. I don't know. In another lifetime, perhaps I would have been a sociologist of science. I find how knowledge is not in the, I mean, yes, in the epistemological sense, but also in the sort of social construction of knowledge sense, how it is that a field comes to a point and how certain methods are propagated and adopted. And it's happening real fast in NLP. Slot intent gate mechanism. Oh, and this is, I think, will be an interesting point for Popping Tonic as well. And actually, I can really quickly post the link to the paper, which is in the YouTube description. I want to intercept the message, DSI says. I don't know what you mean by that. The forum is the Rasa forum. It is forum.rasa.com. I'm pretty sure that one. Yeah, forum.rasa.com. Specifically, we build an open source framework for building conversational AI and chatbots, which is why this is relevant. Slot intent gate mechanism. Enrique's helping out. Thank you, Enrique. In addition to parameter and state sharing, a separate network with a slot gating mechanism was introduced by Gu et al. I'm gonna feel so bad if that's not said Gu, to model the interaction between slot filling and intent classification more explicitly. Figure 1 middle. In the encoder, a slot context vector for each time step, CSI, so context for a specific slot at a time step I, and a global intent context vector, CI, context for the intent, are computed using an attention mechanism. Citation for attention. Ooh, I haven't seen that. The slot gate, GS, is computed as a function of CSI and CI. GS is sigma, I don't know where the V came from, tan CSI plus the weights, and then the dot product with the intent. I don't think this matters a whole bunch. Like, I'm not gonna implement this. Then GS is used as the weight between HI and CS to compute the labels for the slot as follows. Okay, so here HI is so this is the output of this, the gating slot, and this is the context at a specific time point, and HI is ... Perhaps it's in the figure. Softmax, WHI plus gating, and the dot product of the context vector. Larger GS indicates a stronger correlation between the vector for the slots. The vector for the slots and the intent. Okay, so this is just creating a relationship between, I know this is in the attention paper, and I'm sure they're just taking it from there, but I don't remember what it is anymore. So this is basically just a relationship between a specific slot and a specific intent at a given time point. All right, so here is the representation of this. So we take our input sequence in, a bi-LSTM encoder is used to turn it into numbers, basically. And then we have attention over the slots, intention over the intents. So this is a sequence level, and this is at each token. And then at this point, we take the intent label. And then the slot gate is used to, create a relationship between the two. And then softmax is used to produce the slot label at each time step. It must be distributed over each of the time steps. Yeah, so it's a slot label for each of the time steps. E et al. 2019 propose a bidirectional model, SFID, slot filling intent detection network, sharing ideas with Gu et al. With two key differences. First, in addition to the slot-gated mechanism, they add an intent-gated mechanism as well. Second, they use an iterative mechanism between the slot filling and intent detection network, meaning that the gate vector from slot filling is injected into the intent detection network and vice versa. Okay, so if we were going to add these changes to here, there'd be a slot gate here, and there would also be an intent gate, yes, here? Or, yeah, because this, you can't have this just for the slot, because this mediates the relationship between the two. But this is the effect of the intent on the slots, and not the effect of the slots on the intent. So from the attention, there must be a slot gate over here, and then an intent gate over here, and then both of them feed up into those different ones, and then the label happens after the gating. Must be how that's done. Second, they use an iterative mechanism between slot filling and the ID network. Yeah, meaning that they're each injected into the other. Okay, so you have the attention, and then they're just sort of like, each of them is shoved over into the other one, so that the gating is not only affecting the classification for the slots, it is also being moved over for the intent detection, and the intent detection gating is also being used for slot detection. So there's more sort of cross-pollination between the two. This mechanism is repeated for an arbitrary number of iterations. Compared to GU, the SFID network performs better in both slot filling and intent classification on ATIS and SNPs. These are two data sets that they discussed earlier. Amina says, question, is diet a pre-trained model? I don't understand how we can compare it to BERT, especially with Rasa, where we can use both at the same time, and compare them both. And there's some analysis that says diet outperformed BERT. How? Since they don't do the same thing. So BERT is, if you haven't used BERT before, BERT can also be used for classification. So generally it's used as an encoder to take words and turn them into numbers, and that's sort of the intended purpose. But one of the things that you can do is you can add a word, a ghost word, if you were, that has a label in it. And then when you have the output, you can take the value of that ghost word, treat it as the label, and then use that for classification, which could be done, for let's say intent classification. So you can use BERT for intent classification. Diet is not pre-trained, it's an architecture. We may have a pre-trained example for Diet, but I believe when you train your Rasa assistant using Diet, it is using as input some sort of encoded value. Those might be pre-trained, but then the model weights are, I believe, randomly initialized and then updated as you train your assistant. So when you look at your, when you train an assistant and you'll see sort of like the scrolling text, you'll see like diet, blah, 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 epochs, and then like the little bar that goes over it, that's your diet model being trained. And I believe that I know we just read the paper and I don't remember all the details of the evaluation, but the way that you would sort of compare the two, or the way that I would do it is, I would take BERT, I would sort of train a little layer on top of BERT using a specific data set, and then I would train Diet using that same data set and then see which did better. And I'm pretty sure that's what they did in the paper. I know we just read it, it's gone. I know where to look to find it, so I didn't think it was important enough to remember. Yeah, so that's sort of the idea there. And the way that you can combine them is that you can take the encoding, the embeddings from BERT and use those as input to your diet model. Yeah, I hope that helps clarify sort of the difference. You can also, if you are using iterative training in Rasa, you can also have a diet model that you've trained, and then every time that you add new data and you retrain, instead of re-randomizing the weights and then updating them, you would take your current weights and you would update them given the specific data so far. Let me know if that made sense. If not, yeah, we can talk about it a little bit more. And I think that it's very relevant because the papers that we're talking about here are doing sort of the same thing as Diet is. Good questions, Mina. The work from Lee et al. Is also similar to Gu et al. With two differences. First, they use self-attention mechanism, so this is a transformer paper, to compute their the slot labels at each time point. Secondly, they use a separate network to compute the gate vector GS, but the input of this network is the concatenation of the slot label and the intent embedding. Okay, so you take slot label, the intent embedding, you stick them together, you send it through the gate. And GS is defined as tan of the weights, blah, 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 blah. B would be the bias probably for S. Yeah. After that, HI is combined with GS through element-wise multiplication to compute YSI as follows. I'm not going to read that. They report a plus 0.5% improvement on slot filling over Louvan lane. A recent work by Zhang et al. Further improves the performance of BERT-based model by adding a gate mechanism to the BERT model. Table 3 compares the performance of the joint models. Amina says, yes, it helps, thanks. Fantastic. Ravi says, what is the best use case of GPT then? Its architecture is the opposite of BERT. If you were asking me for my personal opinion, I generally don't think large language models are actually that interesting. There's a very small number of things that I would use them for, and it's mostly like toy projects that are like fun but have no consequence because of the fact that you can't really control the output. So that's my stance on it. All right. And that is this one. This is the CLS, the ghost token I mentioned that has the label in it. So this would be the label, and then at the end you would use that one to determine your intent. And yeah, it's just a bunch of transformers stacked on top of each other, transformer encoder layers stacked on top of each other. So very straightforward extension of the transformer architecture, if that's one that you're familiar with. I would consider it a straightforward extension. Let me put it that way. And then table 3 compares the performance. So this is all of the sort of joint models that they're talking about so far. Here they're sharing parameters and state. So this means that the weights are being trained together. State would be sort of knowing about other things in the sequence or the sequence label. And just looking at these, it looks like the transformer BERT model does pretty well. It looks like this token level intent classification plus self-intention does pretty well. So this is the one. So actually, I think, I'm not saying the Chen et al. Paper is bad. It's just not sort of cool, interesting, and different. I think this quick paper is really interesting, that they're doing this intent classification at the token level. And it looks like it works pretty well for both ADIS and SNPs. And I think we talked about last week that ADIS is a task where they're kind of close to ceiling, like folks are doing pretty well at it. State sharing, Wang et al. Doing pretty well, actually better than BERT. And then the slot intent gating is also doing pretty well. So just sort of like as time goes on, numbers go up, which is sort of generally how published papers work. Although I will, word of caution here, I don't know if you've ever heard about like the file drawer problem, but the papers that get published are not necessarily a good sample of all of the papers that get written. And generally papers that say, hey, look, our numbers went up, are the ones that get published. Particularly with transformer models, particularly with BERT models, I would not be surprised if many of the models that were trained ended up being worse than other models. And that's particularly because BERT especially has this problem where some runs are just degenerate. Like some starting weights will result in a BERT model that sort of never converges, just like is always bad and never ends up in a good place, in terms of sort of the final space that your model's walking around trying to find the lowest spot on, to think of it in that way. And that seems to be much more of a problem than it is with RNNs and LSTMs. So my guess would be, just thinking about like all the models that have been trained for this, that even though some of the highest performing models are BERT models, I would also guess that a lot of the lower performing models that you didn't hear about because they didn't get published, maybe because they didn't even get written up because the authors, like researchers, tried it and were like, oh wow, this don't work, would be also in that sort of bin of models. There's actually a workshop ACL workshops don't always happen at the same conferences. They sort of, every year you propose your workshop, and if it gets accepted again, it gets assigned a conference. But there was a workshop on negative results that was really interesting. But as far as I know, that's really the only place to publish work where like, hey, this didn't work, don't do this. So even if over time you're like, hey, this approach is getting better numbers, that doesn't necessarily mean that that particular approach is always going to get better numbers. It means that of the sample that you have, the numbers happen to be reported for, it got better numbers, if that makes sense. So there is a little bit of like, I think if a modeling approach has a very high variance, a leaderboard based approach won't catch that. Anyway, just something I'm saying. I hope that makes sense, and it's just true of using leaderboards. All right, takeaways on joint, slot filling, and intent classification models. The overall performance of joint models for slot filling and intent classification, Table 2, is a competitive with independent models, Table 3. The advantage of joint models is that they have relatively less parameters than independent models, as both tasks are trained on a single model. And also, you get the ability to take the information from one thing and apply it to the other task, since in this case they are not independent. When computational power is not an issue, fine-tuning pre-trained models such as BERT is the way to go for maximum performance. Hybrid models, I should say BERT itself is pre-trained, so if you are using a pre-trained BERT model, you probably are not going to be using one of the ones that was created with a degenerate run. But there's a big section of the BERT paper, they talk about it. Hybrid methods combining parameter and state sharing plus intent gating yield the best performance. For non-BERT-based models, using state sharing is the best on ADIS. However, the disadvantage is that it is actually a bi-model and not a single model. So you get two models there, so you don't get sort of the benefits of having fewer parameters overall. Hello, Habib. What would be the best model for output functions for loss other than softmax? Because Rasa throws the warning, model confidence is set to softmax. It depends. So softmax is usually used when you have a number of labels, and each label has been assigned a probability or a confidence score, and you look for the one with the highest probability or the highest confidence score, and that's what you output. But like that only works for multi-class classification, right? So for things like binary classification, you usually use things like other things, or you could use, a vote instead of softmax. So it depends. The fact that you're getting that error, I mean, if it's a warning, you might be fine. But if it's an error, I would post about it on the forums. Time for my animation. Forum. The bird's name is Sarah. All right. For non-BERT-based models using, we read that. Similar to independent models, contextual information is crucial to performance. Which if you just think about conversations, that's true. Context is important. Also by context here, they mean other text produced in this course of the conversation and not things like social context, which is also important. Adding a self-attention mechanism to either parameter and state sharing or to slot intent gating can boost performance even further. When sufficiently large in-domain training data is available, that's a win. The slot filling and intent classification performance in ADIS and SNPs is already saturated. Therefore, further research on this classic leaderboard chase is not worth it. We will discuss more about that in section 6. Yeah, like I mentioned that we had mentioned last week, they're getting pretty close to ceiling on this one. So a harder data set would be more helpful. Most of the work on joint models is also independent models reports F1 score for slot filling performance. However, these scores do not reveal in which specific cases these models behave differently, contributing to overall performance. I hear somebody asking for an error analysis. That's music to my ears. I love error analyses. I think they're an extremely important part of reporting results, but they don't always happen, particularly in ACL papers, partially because, social norms and partially because of the really short page limit. We leave further analysis on model performance as a potential future work. Yeah. Get in there. See what's going on. All right, scaling to new domains. I think we can finish the paper today. I'm really enjoying this paper, by the way. It's really well written. So far, the models that we consider in section 3 and section 4 are designed to be trained on a single domain, e.g. banking, restaurant reservation, and require relatively large labeled data to perform well. And I would say this is what we focus on Rasa as well, task-oriented dialogue systems that do one thing, because generally that's what people need, particularly corporate customers. In practice, new intents and slots are regularly added to a system to support new tasks and domains, requiring data and time-intensive processes. Hence, methods to train models for new domains with limited or without labeled data are needed. We refer to this situation as the domain scaling problem. So the way that we would deal with this in the Rasa approach would be conversation-driven development, if you've heard us talk about that before. And basically this is the process where people are using your assistant. You are also, while the assistant is live, going through and annotating conversations, correcting errors, adding labels, retraining your model, redeploying, and having that model updating and analysis and labeling and correction as part of your CI/CD, maintenance process. Transfer learning models for slot filling and intent classification. A common approach to deal with domain scaling is transfer learning. In the transfer learning setup, we have K source domains, these ones, and a target domain, and we assume abundance of data in the source domains and limited data in the target domain. Instead of training a target model for the target domain from scratch, transfer learning aims to adopt a model learned from the source domains to produce a model on the target domain. Transfer learning is typically applied with various parameter sharing and training mechanisms. For slot filling and intent classification, two approaches are proposed, namely data-driven and model-driven. As for data-driven techniques, typically we combine data from the source and target domains, and we partition the parameters in the model into parts that are task-specific and parameters that are shared across all tasks. So like adding like a little layer on top for task-specific tuning. Some studies apply the technique using multitask learning. Okay, so I think that multitask learning and joint learning, these authors would consider separate then. So it sounds like for joint learning, they are specifically talking to sharing states or sharing parameters, and multitask learning here is more about diversity in the training data, potentially. And the models are trained simultaneously on the source and target domains. Results have shown that multitask learning is particularly effective relevant to single task learning when the data in the target domain, is scarce, and benefits over single task learning diminish as more data is available. Yeah, so this is what I was talking about with the multilingual BERT thing. Another technique that is typically used in data-driven approaches is based on pre-train and fine-tune mechanisms. Goyal et al. Train a joint model of FC and IC source models on large domain sources, and then fine-tune it by replacing the output layer corresponding with the label space from a target domain and train the model further. We achieve all the things we can do in conversational AI. If I need to check a bank balance, can I show the robot a balance image? Yeah, so I would call that multimodal conversational AI. And I mean, yes, people are working on it, but it is hard. And the way that I would do that in Rasa is I would probably have a separate API to do the computer vision thing, and then send the labels or the information or some sort of structured data from the computer vision to my assistant using a connector, and then handle it using a custom action. Chidant et al. Also use a fine-tuning mechanism, but the main difference is that they leverage large unlabeled data to learn contextual embeddings, ELMO, before fine-tuning on the target domain. So these are the fine-tuning methods that I mentioned, where you have like a little layer on top, and here they are also in the Goyal, I don't know how to say that. They are also using these contextual embeddings. In ELMO, as I remember, are bidirectional LSTMs to create embeddings, so one left, one right, as opposed to BERT, which is a transformer that looks at everything. And I believe there was a figure, yeah? Yeah, okay, so here are the data-driven approaches where you have, shared models and then separate output layers for your source and target tasks. Domain, sorry. As we need to train from scratch the whole model when adding a new domain, data-driven approaches, especially multitask learning-based, need increased training time as the number of domains grow, because you need more data. The alternative strategy, the model-driven approach, alleviates the problem by enabling model reusability. Although different domains have different slot schemas, slots such as date, time, and location can be shared. And generally in Rasa, location is something that we're talking a lot about, but date and time, we would actually recommend a rule-based approach. So using Duckling, which is a library that I think was originally developed at WitAI, and then they were acquired by Facebook. But we have our own fork of it as well. And this is very robust regular expressions that have been written and maintained by somebody else to extract date and time. In model-driven adaptation, expert models are first trained on these reusable slots, and the outputs of the expert models are used to guide the training of the target models on a new target domain. This way, the training time of the target model is faster, as it is proportional to the target domain data size instead of the larger data size of both the source and target domains. In this model-driven setting, Kim et al. Do not treat each expert model on each domain, source domain, equally. Wow. So they train a bunch of models, and they don't, look at all of them and just consider all of them at the same time. Instead, they use an attention mechanism to learn a weighted combination from the feedback of the expert model. So, there's a specific type of name for this type of paying different amounts of attention to different experts, and I don't remember what it is, but it has a name. Jha et al. Boards of experts? No. Use a similar model as Kim et al. However, they do not use an attention mechanism. For training the expert models, instead of using all the available source domains, they build a repository consisting of common slots. The assumption is that these slots are potentially reusable in many target domains. Upon training source models on the reusable repository, the amount of source models, the output of the source models is directly used to guide the training of the target model. So here you have, a bunch of expert models that you've pre-trained, and then they each give a label, and then an attention mechanism is used to select the correct label. And then this is a zero-shot model. Zero-shot means no training data. While data-driven and model-driven approaches can share knowledge learned on different domains, such models are still trained on a predefined set of labels and cannot handle unseen labels, i.e. not mapped to the existing schema. For example, a model trained to recognize a destination slot cannot be used to directly recognize a slot arrival location for a new domain, although both slots are semantically similar, so they're probably both going to be like locations. For this reason, researchers have recently been working on zero-shot model, trained on label representations that leverage natural language descriptions of the slots. Assuming that accurate slot descriptions are provided, slots with different names, although semantically similar, would have similar descriptions as well. Thus, having a trained model for the destination slot with its descriptions, it is now possible to recognize the slot arrival location without training on it, but only supplying the corresponding slot description. So instead of, providing a bunch of training data for each of these slots, if you've already seen patterns that are going to be relevant in training data for similar slots, if you describe them in similar ways, then you can use that knowledge to detect the new slots. In addition to slot description, other zero-shot approaches explore the value of slot value examples. Shah et al. Show that a combination of a small number of slot value examples with a slot description performs better than just the slot description on the SNPs dataset. So at Rasa, we use examples for learning. We use examples for learning entities, and if the entities and slots directly map to each other, then also they are used for slots, but that is not necessarily the case. Zero-shot models are typically trained on a per-slot basis, meaning that if we have n slots, the model will output n predictions. Therefore, a merging mechanism is needed in case there are prediction overlaps. In order to alleviate the problem of having multiple predictions, Liu et al. Propose a coarse-to-fine approach, where the model learns the slot entity pattern coarsely to identify a particular token as an entity or not. So it's a binary classification problem. After that, the model performs a single prediction of the slot type, fine, based on the similarity between the feature representation and the slot description. So this zero-shot model. Okay, so here is the one where you provide the description of the slots, and that description is used as input at each step to help figure out whether or not a specific token belongs to a slot or not. All right, we're close. We're close. We do have to finish reading this section though. I really enjoy these takeaway sections. I think they're super helpful, and I think I'll probably be referring back to this paper in the future. Both data-driven methods, multitask learning, and pre-trained fine-tuning improve performance when the data in the target domain is limited. Both are also flexible, as virtually many tasks from different domains can be plugged into these methods. As the number, my God, I don't want to update Docker. Sorry, the Docker update on Windows is extremely persistent. I'll get to it eventually, just not in the middle of streaming. Yeah, both are also flexible as the number of domains grow, pre-train and fine-tuning is more desirable than multitask learning. However, fine-tuning is more prone to the forgetting problem compared to multitask learning. When the number of domains, k, is massive, the pre-trained fine-tune approach and model-driven approaches, such as expert-based adaptation, are preferable with respect to amount of training time. So, not having to retrain the whole model from scratch when you have a whole bunch of training data. When there exists k existing domains, when no annotation is available in the target domain, the choice is zero-shot approaches with the expense of providing metadata information such as slot and intent descriptions and having accurate slot and intent descriptions, which is no mean feat, I would say. That can be a lot of work to get that information. State of the art and beyond. Wait, nope, I skipped a section. As typically zero-shot models perform prediction on a per-slot basis, potential disadvantages are model accuracy when there is a prediction overlap, so a token is predicted as belonging to more than one slot, and the model can also be computationally inefficient when dealing with many slots. So it might be helpful if you need to add like 1 or 2 slots to an existing model. It's probably going to be a big pain in the butt if you are trying to add a bunch of different slots. State of the art and beyond. Based on the results in tables 2 and 3, it is evident that neural models have achieved outstanding performance on Addison SNPs, showing that it is relatively easy for neural models to capture patterns that recognize slots and intents. ADIS in particular is already overused for SF and IC evaluations, and recent analysis have shown that the dataset is relatively simple and the room for performance improvement is tiny. A similar trend in performance can be noted for other datasets, such as SNPs, and it is likely the performance improvement can be quickly saturated. However, it does not mean these models have solved slot filling and intent classification or NLU problems in general, rather that the model has merely solved the datasets, and this is a big problem in neural methods research. Nevertheless, there are still a number of issues in slot filling and intent classification that need further identification. So in particular, there's I don't remember if we read it or not. I know I've read it, but there's a paper on looking, I think it's called like, what does BERT really know or something? Looking at a number of different tasks where BERT achieved very high performance and showing that what BERT was doing was picking up on spurious statistical correlations with particular tokens. So instead of detecting negation, it was detecting the presence of the word no. And you might be like, well, Rachel, that's fine. There's lots of ways to negate things without saying no, and there's lots of applications where it is extremely important that you know if someone is turning something down. So anyway, just my point there is that, again, this is another drawback of leaderboard-based model evaluation. Portable and data-efficient models. Instead of evaluating models with typical leaderboard setup with fixed train-dev test splits on a specific target domain, it would also be important to test models in different scenarios so that different aspects of the model can be captured. And also, if you're working in industry or a practitioner, leaderboards are nice. They're not your application, right? They're not actually what your model's doing on the ground. For example, as neural models are data hungry, more work is still needed on transfer learning scenarios where evaluation is carried out with less or without labeled data, zero shot, for a particular target domain. In addition, most models for slot filling and intent classification are evaluated on English, which means that more effort is still needed to make models that work well for other languages. Yeah. I think the Rasa community in particular can attest to this. Other languages are also important. Like, English is cool. I'm a fan. It's my native language, but it is not. Which means that blah, blah, blah. Some recent work have started exploring zero cross-lingual methods, citations, and also few-shot scenarios, and the room for improvement in these scenarios is still large. In short, designing a data-efficient model that is portable across domains and languages is still a challenging problem for the coming future. And personally, I am more interested in a data-efficient model than a portable model because the data that I care about is going to be the users that the data that my users provide, and the likelihood that any random model is going to work particularly well for that particular subset of data is lower than I would like, personally. Leveraging unlabeled data from live traffic. Here we go. Now this is the thing that we think a lot about at Rasa. In real situations, personal digital assistants such as Google Home, Apple Siri, and Amazon Alexa receive live traffic data from real users. This large amount of unlabeled data from live traffic is a potential data source for model training in addition to in-house annotated data. I've got thoughts. Unlabeled live data are likely different from in-house data as they can contain more diverse utterances and are also noisy and irrelevant utterances. So here I think that they're talking about specific, like, pre-trained or pre-collected and cleaned data sets. In this situation, existing methods to tap on unlabeled data, such as semi-supervised learning, still face unique challenges to handle live data. It is worth to note that a bottleneck in this direction is that working on live data in academic settings is not trivial. I mean, it's also very much not trivial in commercial settings. And I think a good example of that would be Tay, if you're familiar, which was a conversational assistant, I guess, a chatbot chit chatbot that was on Twitter that was trained on user data, live, and quickly started saying awful racist things and engaging in hate speech, and was a big problem all around. So I would say it's not trivial in general, and yeah, personal stance, you can't get around data annotation. You're gonna have to annotate more data as more data comes in. Some recent works explore this line of research by applying semi-supervised learning and also data selection mechanisms. I might have to read that paper. That sounds interesting. Generative models. Most of the proposed models are discriminative among a few works carried out for generative models for slot filling and intent classification. So this is sort of applying labels, and this would be, generating stuff. Have shown that a generative model is relatively better than a discriminative model in a situation where the data is scarce. One possible direction for generative models is to apply data augmentation to automatically create additional training data. And we've been working at Rasa on some paraphrasing stuff that might help with this. I don't know that they would call that generative or not. Paraphrasing is generally a separate task. The main challenge for data augmentation is to generate diverse and fluent synthetic utterances which preserve the semantics of the original utterance. I would say semantics is definitely part of it, but also the syntactic form is super important, particularly for user-generated data, because you're going to have, like, the way that I chat to my friends is different than the way that I would talk to y'all. Not that, I'm not being friendly, but I perform language use differently in a professional setting than I do in a domestic setting, for example. So semantics is important, but it's also really important to make sure that you are matching your target domain, your target genre, and that you are still capturing that your data is still a good fit for what you're going to see in production. I really have more of a practitioner's viewpoint at this point. Evaluation of slot filling and intent classification. Intent contribution, that's not what that is. On a more complex data set. Existing neural approaches typically evaluated on single intent utterances. However, in a real-world scenario, utterances may indicate multiple intents in an utterance. Show me all flights from Atlanta to London and get the cost. Or even expressing multiple sentences in a single turn. Yes, sometimes people say multiple sentences in a single turn. Yep. While most data sets for slot filling and intent classification are single-turn utterances, there are some multi-turn data sets that provide slot annotation at the token level, namely Restaurant at K, Taskmaster 1 and 2, and Frame datasets. The subset of the schema-guided dialogue (SGD) dataset used in a bunch of datasets, annotated with slots on the token level and covers 16 domains. In addition, the top dataset introduces datasets annotated with hierarchical representation, and MTOT dataset provides flat and hierarchical representations on 6 languages across 11 domains. So, yeah, single-turn utterances are more common than you might expect for things like virtual assistants. For conversational AI in particular, the sort of projects that people tend to use Rasa for, it's a little bit rarer. Rasa projects tend to be intended to support multi-turn dialogue. Oh, conclusion. Oh, my voice is going. We have surveyed recent neural-based models applied to slot filling and intent classification in the context of task-oriented dialogue systems. I don't know where the ordered came from. We examined 3 approaches: independent, joint, and transfer learning-based models. Joint models exploiting the relationships between slot filling and intent classification simultaneously shown relatively better performance than independent models. And that's what DIET is, right? It's a joint model. Empirical results have also shown that joint models nearly solve widely used datasets, ADAS and SNPs, giving sufficient in-domain training data. Nevertheless, there are still several challenges related to slot filling and intent classification, especially improving the scalability of the model to new domains and languages when limited labeled data are available. And I would definitely agree. That is, that's a challenge, right? And it's a challenge that, y'all Rasa developers are working with every day. So, wow, I'm tired. Good paper, I think very helpful. I think hopefully helps give y'all a bit of a, oh, and there's an appendix about the information here. I think Thai is a good one to include. So English, French, and Spanish are all Indo-European languages, the language family, and then French, Italian, and Spanish are all Romance languages. So French, Italian, and Spanish are extremely closely related. English is also fairly closely related. Thai, I believe Thai is actually the only language in its family, or the most widely spoken language in its family. So I think it's a good one to include in a multilingual data set, because if something works for English and Thai, it's probably going to be pretty robust across typologically distinct languages. Yeah. Good paper, very, very helpful. I especially like the little takeaway sections on each of the different approaches that are, I think, super helpful, help to contextualize the work that's been done. Yeah. Amina says, thank you for staying later than usual. Hey, I wanted to get this paper done. I've got other things I want to read. Particularly, what was that Go paper? Nope, that's not it. I could have sworn it was by So let me find that citation again. Do and Gaspers. Talking about the data selection. Oh, that's probably Do, actually. That's probably not Do. The data selection NLP, cross-lingual transfer learning with data selection for large-scale spoken language understanding. Oh, it's on speech. Interesting. Yeah, so that's definitely something that I think is interesting and definitely worth exploring. And I don't think I've read this paper, so all right. Jira says it's a really good session. Oh, thank you. I hope it helped. I know that it can be super intimidating to come into NLP in particular right now has, an enormous publication rate. And it can be hard to sort of like get a sense of the state of the field, not just the state of the art and what's on top of the leaderboards. All right, thanks so much for joining today. Tomorrow we're going to be continuing to work on live coding, same time, 9 a.m. Pacific. And we will be doing oh yeah, I'm gonna be hosting my Rasa X instance somewhere. I'm thinking DigitalOcean. I need to spend some time working on it today. Actually, let me add that to my to-do list. So we're gonna be doing the first of our deployment segments on getting our FAQ, Rachel FAQ bot up and running, and hopefully be able to start doing some more data annotation soon. Need to add and language. Hopefully be able to start doing some data annotation soon, because that's something that I'm particularly interested in. Thanks for joining, everybody. I'll be back tomorrow for live coding. Oh, new podcast episode went up with Julian Gerhardt, who's one of our Rasa superheroes. And we actually talked a little bit about more about embedded systems and voice than sort of vision multimodal learning. But it's a really good episode, and I hope you give it a listen. It's Rasa Chats is the name of our podcast. Yeah, I'll see y'all tomorrow. Thanks for joining.